So the talk of this, the title of this talk is Residual Learning. I'm Making from Microsoft Research Asia, and this is the joint work with Xiaoyu Zhang, Shaoqing Ren, Qifeng Dai, and Jianfen. So here is a summary of our team in this year's ImageNet and COCO competition. And in summary, we attended 5 main tracks, and we won the first places in all these tracks, including ImageNet classification, detection, localization, and COCO detection and segmentation. And so the basic model is nothing more than just ultra deep neural networks in our experiment up to 152 layers. So and on other tasks, including detection, localization, and segmentation, we surpassed the second place by a large margin. So we are witnessing a revolution of depth. So ImageNet is a very good evidence of this revolution. So in the first 2 years of the ImageNet competition, models are shallow, for example, SIFT, OG, SVM, etc. But the results are not too good, and they are actually about 25% top 5 error. So in the famous 2012, the first deep network comes into the ImageNet challenge and greatly reduced the error by about 10%. And then in the last year, 2 very deep neural networks emerged, which is the GoogleNet and the ResidualNet, both of which have about 20 layers. So in this year, our result is based on very deep, actually extremely deep neural networks, which have about 152 layers. So actually, the deep models are not only for the ImageNet classification task. Now in the computer vision area, the deep neural networks and also the representations learned by this network are the engines of many visual recognition tasks, including, for example, object detection, segmentation, and many other tasks. So here is just an example of the challenging Pascal VOC 2007 object detection benchmark. So before the invention of the ImageNet and the RCN detector, the state of the art is the HAWK and the DPM models, which only has about 34% MAP in this data set. So the ImageNet and the RCN method, which is one of the first deep learning methods of this data set, significantly improved this number to about 58%. And in last year, people found that if you replace the ImageNet with the very deep ResidualNet, it is easy for you to approach a 66% or even slightly higher. So if we use an even deeper network, for example, 100 layer in this work, then we can improve this number to 86%. So actually, the deep networks are the main improvement for this visual recognition task. So here is what deep learning looked like 3 years ago. This is the famous ImageNet, which has 8 layers. So here are the visualization of the models last year, which are the GoogleNet and which are the GoogleNet and the ResidualNet, which have about 20 layers. So here is just a visualization of our model this year. It is not too special, so it's just a lot of layers. It's just that machine. So here is another view of this model. So most of the layers are just very simple. So here comes the question. So is learning better networks as simple as stacking more layers? Unfortunately, the answer was no. So here are some simple experiments on the cytokine data set. which will train some networks which are called plane net. So for this plane network, so for this plane networks all consist of 3x3 convolutional layers. So we just stack a lot of them to consist, for example, 20-layer plane network and a 56-layer plane network. So the experiment just showed that the deeper 56-layer network has higher training error and also testing error than the shallower 20-layer network. So we did more experiments on the Cypher 10 dataset and also on the ImageNet dataset. So on the Cypher dataset, we increased the depth from 20 to 32 and to 56 layers. And we found that the deeper the network is, the higher the error it is. And the higher error is mainly because of the higher training error. The same phenomenon is also observed on the ImageNet dataset when we increase from 18 layers to 34 layers. And actually, I believe the observation is still the case if we go in deeper on the ImageNet, but we did not do that because of limited resources. So this experiment indicates that this is a general phenomenon and it is observed in many, if not all datasets. But this phenomenon is counterintuitive. So now let's consider a shallow model, for example, it consists of 18 layers. And on the other hand, we also consider a deeper model, for example, which has 34 layers. So it is actually very easy for us to have a solution of the deeper model by construction. For example, for those layers in the shallower model, we can just copy these layers to the deeper model. So for the extra layers that are unique to the deeper model, we can just set them as identity. So the existence of this solution indicates that at least a deeper model should have the same training error as the shallower model. And actually in practice, we believe that it should have at least lower training error than the shallower model. So this indicates that the difficulties lies in the optimization. So perhaps now the solvers, for example, SGD or the back propagation in its current way, cannot find a solution when we have a network that is substantially deeper than previous ones. So this is our motivation of proposing the deep residual learning framework. So let's consider, for example, 2 layers in a plane network. So usually we expect these 2 layers to fit some underlying optimal mapping. For example, which is denoted as HX here. So when you have many such layers, you expect each of, for example, 1 or 2 of these layers to fit their own optimal version of the HX. So in our framework, instead of hoping each 2 layers to fit a desired mapping HX, we actually hope this layer to fit another mapping which is denoted as FX. And at the same time, we use a shortcut connection which is an identity mapping that directly passes all the information through and across these 2 layers. And this shortcut, the output of this shortcut connection is added back to the output of these 2 layers. So in this way, we expect the functions represented by these 2 layers, which is fx here, to play as fitting a residual mapping in addition to the identity mapping. So if the identity mapping were optimal, then we expect that it is easier to set the weight as 0 to fit identity mapping by this component. And on the other hand, if the optimal mapping is closer to an identity mapping, and we assume that it might be easier to find some small perturbations in addition to identity mapping. So actually, residual representations are very popular in computer vision. For example, for image recognition and image retrieval, the VLAD and the fixture vectors are very powerful shallow representations. And actually, this representation can be considered as encoding by residual vectors with respect to a dictionary, for example, obtained by k-means. And on the other hand, in vector quantization, the popular product quantization method and one of its variants, which is called inverted file ADC, actually quantize the residual vectors with respect to a causal dictionary. And this method is a very efficient nearest neighbor search method. And in another area of solving partial differential equations about images, the famous multi-grid and also hierarchical preconditioning methods actually solve some residual problems between a coarse and fine resolution. And actually, these solvers are much faster, converges much faster than other solvers that are unaware of the residual nature of the problem. So, although these works are just loosely related with ours, all this evidence indicates that residual representations might help us to better precondition or better reformulate the problem. So next, we are ready to introduce our network design. And actually, there is no design in our paper. There is just one principle, that is keep it as simple as possible. So we expect that our framework should work independent of the specific design of each layer. So in order to show its effectiveness, we just use the simplest design, which we follow the style of the VGG paper. So basically, almost all the convolutional layers in our networks are 3x3 convolutional layers. And at the same time, each time we reduce the spatial size of the feature map, for example, by a stride of 2, and we increase the number of filters by a factor of 2. And by doing so, we can roughly keep the complexity of each convolutional layer. So this is just a very simple design, and our purpose is just on investigating going deep. So here are some details about our training algorithm. So basically, in our paper, all the plane and residual networks are trained from scratch. This means that we do not need to initialize from a shallow model, or we do not need any other types of pre-training. And on the other hand, all the plane and residual networks are trained with the help of batch normalization. So actually, batch normalization is a very powerful technique, and it explicitly ensures the variance of the signals. So this means that if you found some degradations in your plane network, we argue that it is unlikely it is caused by vanishing gradient. So the degradation may be caused by some other reasons, but not vanishing gradient with the help of batch normalization. And also, we use some very standard hyperparameters and data augmentations, and all of these details are in our archive paper. So here is a comparison on the 710 data set, and on the left side are the results of the plane net, which I have shown before. And when the depth increased from 20 to 56, the training and testing error both increase. And on the right-hand side are the results of the residual networks, which just simply stack a lot of 3x3 convolutional filters. So when we increase the depth from 20 to 110 layers, and we can see the training and testing error consistently reduced. And so this experiment suggests that the deep residual net can be trained without difficulties, and also the deeper residual nets have lower training error and also lower testing error than the shallow networks. And so here are the similar experiments on the ImageNet dataset. So on the left-hand side are the comparisons between an 18-layer plane net and a 34-layer plane net. And so for the plane net, the deeper one has higher training error. So on the right-hand side is still the comparison between these two residual nets. And we found that the deeper 34-layer residual net have lower training error and also testing error. So in order to going deeper on the ImageNet experiment, we just did a very simple practical design of modifying our component. So instead of using all 3x3 convolutional layers, we decided to use such a bottleneck structure, which consists of 3 convolutional layers between each identity shortcut connection. So the first convolutional layer is the 1x1 layer for reducing the dimension, and the second layer is 3x3 convolution, and the last layer is 1x1 layer for increasing the dimension. So this building block has a similar time complexity as the 3x3 building block. So I believe there are no fundamental difference between these two, but the bottleneck structure just has lower time complexity in terms of depth. So it is easier for us to go deeper. So here are the results on the ImageNet validation set, where we show the results of using 34 layers, 50 layer, 101 layer, and 152 layer residual networks. And we can see that the deeper the network is, the lower the area is on this data set. And this indicates that it is very easy for us to increase the accuracy by just going deeper. So most remarkably, actually, our deep model is not slow. And our deepest model, which has 152 layers, actually has lower time complexity than the famous VGG networks. Actually, I believe this is reasonable. When it is possible for us to go in deeper, then we can expect that the deep models are more expressive than the shallow models. So as a result, it is possible for us to use fewer filters to achieve a good result. So if we can significantly reduce the number of filters, actually it is possible for us to reduce the overall time complexity of the deep model. So basically, this is the result in this ImageNet competition. Actually, this is not the formal competition. This is the classification result. So our result is 3.57 on the validation set. So in my understanding, the merit of the ImageNet dataset is not just for this 1,000 plus classification task. So for the computer vision task nowadays, most of the features are learned from this large data set. So this indicates that if we can have deeper and better features learned from this large scale data set, it is possible for us to improve the accuracy of many other recognition tasks. So features matter. This is the first sentence of the RCN paper by Ross and colleagues. So in this year's competition, here is the comparison between our results and the second place winner. And here are the results of the ImageNet localization and detection and COCO's detection and segmentation task. And we can see that we outperformed the second place by a very large margin from, for example, 11% in relative to 27%. So actually all these results are obtained by the features from the 100-layer residual net. So this indicates that the features learned from a very deep neural network are just easily transferable. So these results demonstrate the power of the features. So I believe it is impossible for any single trick or hack to improve all these tasks except features. So I believe this is the main reason why we can win all these tasks, and just because we have deeper and better features in the data set. And so, for example, on the very challenging ImageNet detection task, we are better than the second place by 8.5% in absolute. So next, I will just briefly introduce our object detection system. So actually, it's very simple. It's just faster RCN system plus the residual net. So here is a brief introduction to the faster RCN system. Given an image, we use the convolutional layers to extract a convolutional feature map. And after that, on this feature map, we use a fully convolutional region proposal network to extract proposals. And these proposals will be used to extract feature map regions. And these feature map regions will then be classified. So the entire detection system has no external modules. There are no selective search, no HBox, no MCG. So everything is just done by convolutional neural networks and deep features. So this is the comparison of the baseline result of the baseline faster RCN system on the COCO dataset. So using the COCO metric, the VGG16 has a result of 21.5%, and our result is 27.2%, which is a 28% relative improvement. And this improvement is just because of the deeper features. No parameter, no other tricks, no other hacks, just because of features. So as I mentioned before, the region proposal network learn proposals from the data by extremely deep networks. And as a result, actually, in all the entries in this year's competition, we use only 300 proposals per image without the help of any external modules. And actually, we find that the external modules does not help in our case. And also, we add what is just missing in the faster RCN system. For example, iterative localization. It seems that every team uses this. And context modeling, 2%. And multi-scale testing. So I believe these are very common traits of improvement. And actually what is important is that all these modules are based on the same deep features learned by the deep networks. This means that if you have a better feature, you can do each step slightly better than the shallower feature. And if you have many steps, for example, proposals, detectors, localization, context, or feature, then each step you can do slightly better than your shallower network. This will give you a cumulative gain just because you have deeper features. So here is an example result on the COCO dataset. There are too many objects here, so let us carefully check. So this is a knife, which is very small. This is glass, another knife. And so here is a person with some partial occlusion. This is another person. So this is a plant in the background. So this is a big dinner table. Has many objects. So here is another example on the COCO dataset. So this is a person which has very poor lighting on the background, a refrigerator, an oven which is partially occluded, and some small objects like two bowls, a cup, a knife. And here is just another example. So this is an umbrella, a dog, a truck that is only partially seen, and a motorcycle that is partially seen. So these are some interesting examples from the COCO dataset obtained by our method. And also, on the other hand, I would also like to briefly introduce our instant segmentation system. So the basic idea behind the instant segmentation system is very similar to the faster RCN system. That is, we expect to use convolutional neural network to solve all the problems in this system without using any external modules. So we formulate this problem as a multitask cascade structure. So in the first task of this cascade, we propose a box level region. And in the second task of this cascade, we regress mask level regions from these boxes. And after that, we classify each mask. And we formulate this as an end-to-end system, and we propose an algorithm to exactly train this system. And so the key behind this exact training is a differentiable ROI walking layer, which is actually differentiable with respect to the bounding box coordinate. So here is just one example of our semantic segmentation system. And we can see that there are some very small objects here, ski on the background. Ski is one of the most challenging categories in this data set. Also, there is a car here. So in conclusion, we have some lessons from this work. The first lesson is that deeper is still better. At least we found that this is still true when we go to 152 layers. Another very important lesson is that features matter, and actually features still matter when we go that deeper. And finally, it is an advertisement. I would like to say that fast RCN is just amazing. Because if you can learn everything just from the convolutional neural network, then it is easier for you to obtain more accuracy gains just from a better network or more training data to train your better network. And finally, I would like to thank my amazing team, including Xiangyu Zhang, Shaoqing Ren, Jifeng Dai, and Jian Sun. And that's all with presentation.
Great. So, are there any questions?
Good question there for the features. You guys can apply some dense features that the others
So in my understanding, perhaps you can visualize the features using, for example, Zeta and Ferguson's method. But on the other hand, the effectiveness of very deep neural network, for example, when you go from AlexNet to VGG, the effectiveness is mainly empirical. So I mean, we have many empirical results to support this so-called conclusion or observation.
One down there. So how much deeper do you think we can go, and what are the physical limitations we have currently with the 150-layer models?
Yes, and actually the main obstacle for us to go deeper is the memory of the GPUs. So we have done a lot of engineering work to optimize the memory management. So each time we can improve it, so we can go deeper than previously. So 152 layer is the deepest network I can train based on my implementation and based on our GPU memory. So actually, I also trained a 200-layer network on the ImageNet data set, but because of the memory issue, I have to reduce the mean batch size, so the result is not directly apple-to-apple comparison. But the result of the 200-layer network is still quite good, so which indicates that at least the optimization difficulty has been partially solved. But on the other hand, if the optimization is not the first issue, then the next issue should be the generalization issue. So when the model is getting deeper, it has more parameters, and for example, even the ImageNet data set maybe is insufficient to train these large models. So so I believe perhaps 100 layer or 150 layer is a good balance between the current data set and the current physical memory of the GPUs.
Do you have fully connected layer?
There is no hidden fully connected layer.
There's no fully connected layer.
There is just one, which is the final 1000 classification layer.
But do you drop your dimensionality before the fully connected layer? Because it seems like you're going up, you're swapping planes by resolution. So
yes, so
it's gonna be very big before the fully connected layer if you don't drop stuff.
no. So finally, we use a global average pooling layer to put everything together.
Right.
But I have tried to remove this layer, and actually the result is very similar.
And then one last question: what about training time? You disclose that?
Yeah, so the complexity of our deepest model, which has 150 layers, is only about 50% of the VGG network. So this is the time complexity. But because of some other practical issues, for example, we use batch normalization, and also because we have many layers, so the computations are not very parallel. So in practice, each iteration is roughly the same as the VGG net. So this means that in our practice, it usually takes us 2 to 3 weeks on a GPU to train the network.
Thank you.
Jen here and then in the back.
I was wondering about visualizing the difference in your deepest networks from data set to data set. So that slide, I love your slide about saying, how do you do weekly, how do you we're saying, in the worst case, you base learn by your repeated layer, which is 0, and you have identity, and otherwise you learn these ways. How do these change as the network is deeper?
So actually, the way it changes is not too different from the plain network. I mean actually, when the training evolves, the changes of the weights of all layers are roughly similar. Yeah.
Down there will be the last question. Do you know already how often this identity mapping really happens, or in other words, the weights between the shortcut connections goes 0?
I cannot quite hear your question.
Do you know already how often this identity mapping really happens? Or in other words, how often the weights between the shortcuts go to 0?
So in our network, the shortcuts are the network structure. I mean, the networks are built with the shortcut connection. So I don't know what you mean by how often it happens, because
but if the weights go to 0, the net only use the shortcut connection.
So I have some experiment, some analysis in our paper. So in practice, we find that the deeper the network is, the smaller the responses of the weighted layers are. So I mean, when you have more layers, each layer will do less modification.
Great. So let's thank the speaker again.